This is Appendix D, page 1, where we're going to review graphing techniques. We'll start off by drawing graphs of basic functions, and then we're going to be stretching and shrinking them, reflecting them across the x and the y-axis, testing for symmetry, and then graphing translations of the graphs. So the first one is to graph f of x is equal to 2. And we can just make little tables to help us to graph these. Do you see how f of x is the same thing as y and it's always 2? So I'll just put 2's for the y's, and x could be anything. So I'll just choose other values for x. Now if I plot 0, 2, it's on the y-axis, 1, 2, and negative 1, 2, you can see that we have a horizontal line that passes through 0, 2. The identity function is whenever x and y are the same. So to graph this one, I'll choose 0, 1, and negative 1 for x, and then y has to be the same thing. So if we plot these points, you see how this line is just cutting quadrants 1 and 3 in half. And then the absolute value function is kind of like the identity, and it's the same as the identity when x is positive, but when x is negative, do you see how y is just the opposite? So we'll still have 0, 0, and 1, 1, but if x is negative 1, then y is going to be positive 1, because the absolute value of a negative number is positive. And so when we graph this one, we have the first quadrant cut in half, but then the second one is also, so the graph is a V-shaped. The quadratic function, I don't know if you remember, it's a parabola. So we could plug in, say, negative 1, 0, and 1. If we do this, we are going to have the same values as the absolute value. So you probably want to choose other values for x like 2 and negative 2, and then you'll see that you're going to get 4 for those. So if we plot these points, you can see that looks just like the absolute value function, but if I choose 2 for x, then do you see how y is 4, because 2 squared is 4? So this is the graph of a parabola. The square root function, well, for this one, x cannot be negative because the square root of a negative is not a real number. So lowest value you can have for x is 0. Square root of 0 is 0. Square root of 1 is 1, and then square root of 4 is 2. Do you see how I'm choosing numbers that are easy to find the square root of? So we have 0, 0, 1, 1, and then 4, 2. So for this graph, it starts at 0, 0, and then it keeps increasing. The cubic function, if I choose negative 1, 0, and 1, well, negative 1 cubed is negative 1, 0 cubed is 0, and 1 cubed is 1. So if we choose negative 1, 0, and 1, you can see that it looks like it's going to be a straight line. But if I choose 2 for x, 2 cubed is 8, so that's way up here. So we have a curve. Negative 2 cubed is negative 8, so it's very steep in that direction. The cube root function, well, we could just switch our x and y values of the cubic function to get this, but if I plug in negative 1, 0, and 1 for x, we're going to get the same values for y, because the cube root of negative 1 is negative 1, cube root of 0 is 0, and cube root of 1 is 1. So this, again, looks like it's going to be a straight line. However, if we plugged in 8 for x, do you see how the cube root of 8 is 2? So that's going to be way out there. So that's the cube root function. So those are some of the common graphs, and you're going to be working with these graphs on your homework and then doing some stretching, shrinking, reflecting, and translations of the graphs. So for example 1, we're asked to stretch and shrink, f of x is equal to the square root of x. So if we look at the square root function, that's this one here, we're going to be working with that graph for all 4 of these examples in example 1. So for the first one, do you see how there's a 2 in front of the square root of x? So what that does is that just takes your x's, when you plug your x's in, you get your y's, but then you're going to multiply your y's by 2. So if I have 0, 1, and 4 for x, well, 0, the square root of 0 is 0, times 2 is 0. Square root of 1 is 1, times 2 is 2. Square root of 4 is 2, times 2 is 4. So let's see what happens with the graphs. 0, 0, 1, 2, and 4, 4. So it is a curve, but do you see how it's stretched vertically? Because the y's are being multiplied by 2. Now for this one, we have 1/2 is the coefficient, and so we plug in our x's to get our y's in the original function, but then instead of getting 0, 1, and 2 for y, we're going to get half of those. So we have 0, 1, and 4 for x. If I plug in 0 for x, I have 0 times 1/2 is 0. Plug in 1 for x, 1 times 1/2 is 1/2. And if we plug in 4, the square root of 4 is 2 times 1/2 is 1. So plotting these points, you can see that this is shrunk vertically. So this graph is shrunk vertically, and that 1/2 is what does it. Now it gets a little more complicated when you have a number that's inside of the radical. So what I'm going to do when I make a table is I'm going to force it so that my y's stay the same, though my y's stay as 0, 1, and 2. And you'll see why in just a minute. So if I plug in 0 for y, do you see how x has to be 0? If I plug in 1 for y, then x would have to be 1/2, because 2 times 1/2 is 1. And if y is 2, x would have to be 2, because 2 times 2 is 4, the square root of 4 is 2. Now if we plot the points, we have 0, 0, and then 1/2, 1, and then 2, 2. So it has a similar curve, but do you see how this 2 is in front of the x? This took the graph and it shrunk it horizontally. So it shrunk the graph horizontally. You'd think it should stretch it because the number is greater than 1, but when it's greater than 1 and it's inside within the radical, then it actually shrinks it. So can you guess what would happen in the next one if we have 1/2? If I wanted to keep my y values the same, 0, 1, and 2, then if I plug in 0 for x, you can see we're going to get 0 for y. In order to get 1 for y, we have to plug in 2 for x. And to get 2 for y, I need 1/2 of, that would be 8. 1/2 of 8 is 4. Square root of 4 is 2. So if we plot these points, we have 0, 0, 2, 1, and then 8, 2 is way out here somewhere. And you can see that this 1/2, this stretched it horizontally. So stretched the graph horizontally. So let's look at what happens in general for stretching and shrinking. Suppose that we have a function y equals a times f of x. So if a is greater than 0, if there's a point xy that lies on the graph, then the point x, ay, lies on the graph of y equals a times f of x. Now if a is greater than 1, then the graph of a times y equals a times f of x is a vertical stretching. Of the original graph. If a is between 0 and 1, then it's a vertical shrinking. So the vertical stretching graph that we did, was this one here. F of x equals 2 root x. The vertical shrinking was this one here. And then for our horizontal stretching or shrinking, do you see how we have y is equal to f of a times x? And so this is a little tricky because remember how we chose what values we're going to have for y? And then to get the new x value, we had to take x over a. And then if a is between 0 and 1, then we have a horizontal stretching. And this is in this last example. So here we had a horizontal stretching. You see that 1/2 is between 0 and 1. And for the last one, if a is greater than 1, so that's this one here, then we have a horizontal shrinking.